So this is mostly application agnostic. Okay. There are a few statistics examples. So in the statistics part, we use I don't know how much I'll have a time to get to, but for the statistics part, we do work with real world data. Data of, for example, city sizes, populations of cities, income data, from the census you get some population data. I'll talk about records. So intervals between records that are found, some extreme occurrences and so on. So in many of these cases, we do end up using. So in the book, for example, a lot of illustrations are based on data available from data sets all over the place, including electricity grids and so on. But I don't know how much of that I'll get a chance to present.
All right. So you will be providing a link for your the book. You said that
it's
separately.
I'll probably write down the link. But if you just search, on my webpage, there's a link to where you can download it from. Do we begin? Okay. So far we have talked about we are still talking about properties of heavy tail distributions. We talked about scale invariance, asymptotic scale invariance more precisely, which corresponds to the class of regularly varying distributions. We talked about the catastrophe principle, which defines the class of sub-exponential distributions, and we talked about how these classes are related to one another. Right? Now there is a final third class of distributions that I would like to introduce, and I'm going to motivate that via this thought example. So you can look at the slide now. So the question I ask is, as you wait for something, what happens to the expected or the distribution of the residual waiting time in each of these scenarios? The first of these scenarios is waiting for a table at a restaurant, right? As I wait longer, after having waited a while, what happens to the distribution of how much longer I have yet to wait, right? For a bus, right? I've already been in the bus stop for 20 minutes. What's the distribution of how much longer I have to wait until the bus comes back? Or response to an email, right? I sent an email 3 days back to my advisor. I haven't gotten a response. What is the distribution of the residual time until it hear back? So it turns out that these are qualitatively quite different, right? One hopes that when you are waiting for a restaurant, the distribution in some sense, and I'll make this precise going forward, the distribution of the residual waiting time should hopefully shrink with the time that I have waited, right? I've waited a while, the time I have to wait now should shrink. With emails, you sometimes may have noticed that if after a while you haven't gotten a reply, you're probably never going to reply. You get a reply at all, right? You see that in these different contexts, the manner in which residual waiting time or residual life behaves is qualitatively different. Okay, so here is how you can think of the distribution of residual life. So suppose that F describes the distribution of the total waiting time. Okay, and I'll also interpret this in terms of lifetimes in just a bit. For now, think of it as a waiting time. Now, given that you have already waited X amount of time, what is the distribution of the remaining waiting time? In other words, condition. So that's what we are denoting by R sub X. So what do I mean by R bar sub X of T? This is the probability that I have to wait, T more units of time, given that I have already waited X units of time. Okay. So given that the random variable, let's say capital X, which is associated with waiting time, is greater than little x, what is the conditional probability that the random variable is greater than x plus t? That's the distribution of the remaining waiting time. Okay. So let's look at a couple of examples to motivate this. If the underlying distribution f were exponential, then the distribution of the residual waiting time is identical to the distribution of the original waiting time. That follows from the memorylessness of the exponential, right? So this we know. Now let's do this calculation for the Pareto, right? The only reason I've said Pareto is because this F bar has a very clean form for the Pareto, so I can just plug this in exactly and give you a clean closed form description of what the distribution of the residual waiting time looks like for the case of the Pareto. Okay, it has the form 1 plus t by x raised to minus alpha. Okay, so now fix t and look at what happens as x becomes large. What is the meaning of this? Given that I have already waited x amount of time, what's the probability that I have to wait an additional t units of time? And what happens to that as x becomes larger? Note here that as x becomes larger, this thing is actually growing, right? Which means that as the time that you have waited increases, the probability that you have to wait an additional t units of time increases and increases all the way to 1 as x becomes large, as x goes to infinity. Sorry. Yeah, so increasing in x. So you see some very, this property is very different from the property you might expect from light tail distribution. So try doing this, for example, with a Gaussian or, those of you who are comfortable with hazard rate, many distributions that you are used to have a hazard rate which is decreasing. I'm sorry, it's a hazard rate which is increasing, right? So but here you are actually seeing that the fact that I have waited for more than x actually increases the probability that my waiting time is going to be even further higher, right? Another interpretation to this comes if you think of x as a lifetime, right? Think of x as being how long I've lived, right? So what's the way to think about this? Given that I have already, what is x? My lifetime being greater than x means that x years have passed since I was born and I'm not dead yet, right? So given that I have survived x years, what's the probability that I'm going to live for another t years, right? If my lifetime were exponential, which it is not, then the distribution of my residual life would be insensitive to my age. If my lifetime were Pareto, which also unfortunately it is not, the probability that I will live an additional t years is actually growing with my age. So as I become older, the probability that I will survive another t years is actually increasing and approaching 1 as my age increases, right? So this is rather counterintuitive property, which in this case we have verified for the case of the Pareto. Okay, so let me introduce you to a couple of ways in which we think about residual life. So you may have encountered these in your past work. So one way to think about the residual life distribution is via its mean. As the name suggests, it's a mean residual life. Given that I have survived x units of time, what is the expected residual life that I have? Just the expectation associated with that distribution, right? And there is hazard rate. Hazard rate, so that's the definition of expected mean residual life. The hazard rate, for those of you who have seen it, is defined for continuous distribution as a ratio of the density to the CCDF. Okay, the way to interpret that is basically the density of the residual life function at 0. So roughly speaking, the hazard rate captures, given that I have lived X amount of time, what's the probability that I'm going to die in the near future? That's kind of what is being captured by hazard rate. Okay, so you might, this is not precisely true, but many heavy tail distributions tend to have decreasing hazard rates and increasing mean residual lives. Right? That's consistent with what I said with respect to the Pareto. As I live longer, the fact that my probability of immediate death decreases is basically associated with a decreasing hazard rate and an increasing mean residual life. Right? Many light tail distributions tend to have an increasing hazard rate, which means the probability of death in the near future keeps increasing with your age and decreasing mean residual life. Right? However, it turns out that these properties are not exactly aligned with heavy tails. Right? Turns out that decreasing and increasing are too strong. Right? You might have seen by now that many heavy tail properties tend to have an asymptotic nature. Right? Increasing, decreasing is too strong across the entire body of the distribution. You're expecting some sort of monotonicity. So it turns out this equivalence is not quite right. Not all heavy tail distributions have a decreasing hazard rate or increasing mean residual life. It turns out not all light tail, there are in fact some light tail distributions that have decreasing hazard rate and increasing mean residual life. Okay, so it's not just the monotonicity of these properties of the residual life distribution that characterizes heavy tails in a clean manner. It turns out that the correct property that captures heavy tail distributions is the following, right? And this defines the class of long tail distribution that somebody was asking about. So F is long tail if you look at the limit as x tends to infinity of the residual life CCDF. What is this? This is the probability that I am going to live another t units given that I have lived x. I'm looking at that as x tends to infinity, right? So I'm fixing the point of the CCDF. The CCDF is evaluated at t, but I'm increasing my age off to infinity. So as x tends to infinity, what happens to that? That is equal to 1 for all t. Okay. What does that mean? That as my age goes to infinity, my residual life distribution becomes degenerate. For every t, the probability that I will survive more than t years is actually going off to 1. Right? So which means the residual life distribution's mass is being pushed off to infinity in limit, and in the limit it's a degenerate. Point-wise, it's a degenerate. Okay. So that defines a class of long-tail distributions that have this property, right? Another way of saying this is the following. So f is long-tail if and only if f bar of x plus y is asymptotically f bar of x. Okay, so this is how you would say. Now, this is true for all y in R. Okay, so this defines the class of long tail distribution, right? So I already explained what it means. Basically means that the residual life distribution is going degenerate as x tends to infinity. You might ask, are there equivalent characterizations of long tail in terms of hazard rate and mean residual life? It turns out that there are. I won't have a chance to get into that, but it turns out that you have to look at asymptotic properties of hazard rate and mean residual life rather than something that's a kind of across the body type property, right? Across the body monotonicity is too strong. So it turns out that subject to some regularity conditions, long tail distributions correspond to those where the mean residual life shoots off to infinity as x tends to 0. The hazard rate decreases to 0 asymptotically as x tends to 0. Okay, so this is the most general way of saying it, subject to minor regularity conditions. This can be restated in terms of asymptotic increasing or decreasing properties of hazard rate and mean residual life. Okay, I won't mention that, but again, these connections can be found below. Right, so they're all these properties of the residual life distribution are related. That's the point. Okay, so again, we see this thing again and again that these across the body type properties are not necessarily the right ones, but suitable asymptotic versions of these actually correspond to the properties that actually lead to this class of heavy tail distribution. Okay, coming back to this picture, it turns out that long tail distributions lie here. The long tail distributions are in fact a superset of the class of sub-exponential distributions and a subset of the class of heavy tail distributions. Okay, each of these inclusions is strict, as I mentioned. So S is a strict subset of L. One can come up with pathological examples of distributions which are long tail but not sub-exponential. One can come up with pathological examples of distributions which are heavy tail but not long tail. Okay, but these are pathological, right? So there aren't interesting or commonly used distributions with heavy tail distributions which are not sub-exponential. Okay.
Heavy tail refers to heavier than exponential. But what longer than some?
No, it doesn't mean it. It just means that the tail is really long, right? Because the tail is not. What does this property mean? That the tail is not decaying, right? F bar of x plus y is practically f bar of x. As x becomes lambda. So I think it just means that the tail lamba chal raha hai types. Right? Okay, so I've already drawn this picture. Yeah, and these are the different properties. Okay, so this brings me to the conclusion of the first part of the tutorial, first of three, where we were going to talk about properties. Now we are going to quickly go over emergence and subsequently estimation. Right, so here I'm going to be a little quicker. There are fewer proofs that I will do, although there are a couple of informative ones that time permitting I will do. Okay. Yeah. So in particular, we will talk about three different mechanisms for heavy tails to emerge. So the first of these is what is called additive processes, right? So many of us, again from intro probability where we study the center limit theorem, think of the normal distribution as being quote unquote normal, right? So in many settings, it's very natural to assume that the distribution of some quantity like noise and so on is Gaussian, right? Because we have been taught that when these independent factors are adding up together, the normal distribution tends to emerge and so on, right? But it turns out that this is not the complete story so far as distributional limits of additive processes are concerned. So there is in fact a generalized central limit theorem which allows for the possibility also of heavy tail limits to emerge. So that's the story I'm going to very quickly go over now. So first order question is, if you have an IID sequence of random variables, how does what I call the running sum from 1 to n of xi, how does that grow? Assume that the mean is finite, right? So the first order answer to this is already given by the law of large numbers, right? Law of large numbers tells you that, that 1 by n times this running sum has an almost sure limit, which is simply the expectation, right? Another way of writing that a little less formally is that the running sum, the first order approximation of the running sum is n times the mean. So this is what I would call the law of large numbers approximation plus something that is a little O of n. Okay. So one can think of the central limit theorem as basically peeling this onion a little further and trying to understand what is inside that little O of n. It's like giving you a second order approximation to this running sum, right? So yeah, this is just an example where if you take the running sum only plot it from 1 to 15, then you get all this funny business. But you take a few more like n equals 300, and this law of large numbers approximation becomes rather apparent. Right? I think these are all from exponential. The individual increments xi are exponential. Right? So yeah, that's what the running sum looks like. And what does law of large numbers tell you? Law of large numbers is telling you that no problem. Yeah. So that's what the central limit theorem tells you, right? So the central limit theorem tells you that the error is of the order of square root n, right? So the way to now, again, this is not a formal way of saying it, but the running sum is given by law of large numbers, first order term, second order term, which is now random, right? That's your that's order square root n plus little o of square root n. Right, so that's one way to think about the law of large numbers and the central limit. Now, the classical version of the central limit theorem that we study has a couple of key assumptions. One of them is the IID assumption. Depending on which book you read, there is a large number of ways of relaxing that IID assumption. That's not really our goal here. The other key assumption is that the variance is finite. Right? You need finite variance for this version to hold. So the question that we will ask is, what happens if the variance is infinite? Are there other distributional limits that you can get to the running sum subject to suitable centering and scaling, or suitable centering and normalization? Right? So it turns out this is now a well-studied thing. So this is just a picture that says what happens if your xi's are heavy-tailed. In this particular case, I believe these are heavy-tailed with infinite variance. You can see that the running sum, it does satisfy the law of large numbers approximation, but you can see that the running sum qualitatively looks quite different. If you're this particular case, this is Pareto, and you have every now and then this sudden jump, which explains most of where the process is, right? And that's kind of similar to what the intuition you get from the catastrophe principle as well, right? One large jump. right? And so that also, it turns out, qualitatively changes the nature of the error signal. The error signal every now and then can have these huge jumps too. Okay, so there is a generalized center limit theorem that tells you under what conditions you can get a distributional limit of, just a moment, this running sum minus a sequence Bn. So you can think of Bn as your centering sequence. In the classical center limit theorem, it's just the mean of the running sum, right? Divided by an. An is a normalization, sequence, also a function of n. In the classical setting, it's square root n. But for a general sequence an and bn, under what conditions will you get a limit? Okay, so this is in fact a well-studied classical problem. The best comprehensive source I'm aware of is basically the Feller. So Feller's book, I think Probability Volume 2, has a comprehensive treatment of this. So it turns out that the class of limits that you can, class of distributions you can get in the limit corresponds to what is called stable distributions, where stable distributions are characterized via their characteristic function. This makes sense because, as I mentioned, for example, most of you, the proof of central limit theorem that you would have studied in intro probability is based on characteristic function, simply because these sums are easier to work with in transform domain rather than what I would call time domain, right? And so this entire class of stable distributions is expressed in terms of the characteristic function. It turns out that that class of stable distributions has one and exactly one, light tail distribution, that's the Gaussian. All the other elements of that class are regularly varying with an index lying between 0 and 2. Right? Index lying between 0 and 2 means that these are regularly varying distributions with an infinite variance. Right? Infinite second moment. Right? And so the moral of the story here is that, if you look at the, if you look at the entire class of limits that you can get from centered and normalized versions of this running sum, the additive process, you get a class of distributions in the limit, of which the Gaussian is one corner case. All of the other cases are in fact regularly varying with infinite variance. You had a question, sorry.
What about case when mean is not?
So that still can be accommodated in this. It's just that, yeah, you will no longer be centering anymore because there's no mean to subtract out. But there is a version of this statement that's even available. Yeah. It's just that in that case, your limit will have an alpha also between 0 and 1. Okay.
Will Cauchy become the corner case then?
Believe I'm not sure if the Cauchy is part of the. I believe you are right. I believe the Cauchy. So in the class of stable distributions, there's only a handful of these that have names, so to speak. I believe the Cauchy is one of them. Yeah. Yeah. So this is how you get a general. This is not quite right. Instead of n raised to 1 by alpha, this should have been an, right? An plus little o of a. So that is what the general story looks like, right? So this is simply to say that in additive processes, you can have heavy-tailed limits emerging, but this is not the most convincing reason for why heavy tails come up in practice, because to get heavy tails in the limit, you have to have heavy tails in X to begin with, right? Because you need infinite variance to get anything other than a Gaussian in the limit, right? And infinite variance means that you started with something that was heavy tailed already. So these X's have to be heavy tailed for there to be a limit in the heavy tail. So they don't explain the emergence of heavy tails. If you have heavy tails, then the limiting distribution you can get from these additive processes subject to centering and scaling can also be heavy tailed, specifically regularly varying. Okay, so there is an entire story of stable distributions which I won't get into, and there is a clean description of these in terms of characteristic functions. There is also a clean proof of a special case of the generalized central limit theorem, which very nicely almost mirrors the classical proof that you're all used to, right? The classical proof one is all used to is based on, essentially, if you can think of it, it's like a Taylor expansion of the characteristic function around t equals 0, right? It turns out, so now that Taylor expansion, if you remember your proof of the central limit theorem, requires two terms. You have to have the t term and the t square term, right? That's where the second moment comes into the picture. It turns out that if that second moment is infinite, there are theorems that tell you what the correct quote-unquote correction term for the Taylor expansion is in such cases, right? And using that different correction term, you can come up with analogous proofs where the limit ends up not being the Gaussian characteristic function, but the characteristic function corresponding to something regularly varying between 0 and 2. Okay. Yeah, that's all I will say about this at this point. As I said, finite variance leads to a light tail limit, but if you have infinite variance, you get a heavy tail. All right. So you can get either normal or power law. I want to answer. So in the context of additive processes and heavy tails in additive process, there is one, I think, more interesting scenario where they come up, and that's the following. Right. I'll explain this in the context of the symmetric one-dimensional random walk. Those of you who have encountered, who have done a course on Markov chains, STQT or whatever, would have encountered this. If you consider a symmetric random walk over the integers, right? So imagine that you are starting, maybe I'll define it here. So you are starting at 0 and xn is equal to xn minus 1 plus yn for all n greater than or equal to 1, where yn is basically going to be IID and you're taking values in 1 minus 1 with equal probability. With probability half. Right. So the way to think about this is that you're a drunk person in an imaginary one-dimensional world starting at the origin, and you're drunk. So at every time step you move left or right with equal probability, and you just keep looking at the evolution of this drunkard's trajectory over time. Right? This is a Markov chain, in fact. But again, the Markovianness is not relevant to what we are asking now. Okay. Now let us ask, what is the return time of this drunkard? Given that at time 0 this person started at 0, what is the time when this fellow comes back to 0 for the first time? So let t be the minimum value of n greater than equal to 1 such that xn is equal to 0. So this is the return time. Okay. Now a priori it may not even be obvious that this t is a random variable. Right? Do I know, for example, that this person is guaranteed to, will return with probability 1? Not yet. It turns out that this is in fact a random variable. So the drunkard in 1D at least, will return with probability 1. And it turns out that the return time is in fact regularly varying. So that's what is written here. So if you look at ignore ruin time, that's in a more general context, just they say return time. The distribution of the return time satisfies this property, that the probability that the return time is greater than x is asymptotically some constant divided by square root x. Okay, so this is a non-degenerate. So this is perhaps the simplest example one can give of a non-degenerate distribution which has an infinite mean, which you can explain quite easily about how it emerges, right? So it's in fact regularly varying with index minus half. So it's not just infinite mean, you know exactly what the index is associated with the power. Okay. So what I wanted to do is maybe spend 10 minutes going over. There are many ways of proving this statement. Okay. If you look at the book, subsequently, the way we do this is via transform techniques. You can actually say something about the Laplace-Dietz transform of this return time t, and there are theorems that allow you to reason about the tail distribution of the function in terms of the asymptotic properties of the Laplace-Dietz transform. So it turns out that understanding how the Laplace-Dietz transform behaves in the neighborhood of 0 gives you information about how the tail behaves as x tends to infinity. Okay, so I won't get into that. I will now basically just quickly run you through what I would call nice, cute time domain based argument for why this is the case. For now, believe me that t is in fact is non-degenerate. You are going to return the probability function. Okay. So to go through this, I need to introduce another problem which is interesting in its own right. Many of you may have encountered this. This is called the ballot problem, or also referred to as the Bertrand's ballot problem. Okay. So the idea is the following: it's an election with two candidates. Right. So there's a candidate A who has P votes. Right. Again, A has probably paid money, whatever. A is going to have P votes. Let's pretend that, right? And B has Q votes. Right. with P greater than Q. Okay, which means we know that A is going to win the election. That's not the question here. The question here is the following: assuming that the votes are going to be counted in random, in a random permutation, what is the probability that A remains ahead? Right, when the election is going on, we keep seeing us candidate is leading by so many votes and stuff like that. What's the probability that the eventual winner, that is A, remains ahead across the entire counting process? Right, so that's the question that the ballot problem asks. What is the probability that A leads throughout? Okay, does anybody know the answer to this? Okay, so then I encourage the students in the audience to go back. You can try thinking about this. It's a, if you want to prove this by analyzing, there's a very neat trick to actually come up with the answer to this, which I will not get into because that's not the agenda of this tutorial. But I encourage you to take a look. It's as elegant a solution as I've ever come across, and it turns out that the answer to this is P minus Q upon P plus Q. Okay, so this is the probability. Go back and check if this intrigues you, and you might think, combinatorially I need to look over all these sequences and do something very hard. It's remarkably elegant. So, what does any of this have to do with return time? Let us see. So, what I want to do is come up with an expression for the probability mass function of the return time, and to do that, I'm going to use the result of the ballot problem. I'm going to take that as a given. I encourage you to take a look at how that is. So note that in this case, the return time has to be even. You can only come back in an even number of steps, right? Because it will be as many left movements as right movements. So what is the probability that t is equal to 2n? Okay, can be written as the probability that t is equal to 2n, and you look at let Sn be the position of the random walk at time n. Right? So S2n is equal to 0. Right? This is harmless, right? Because t equals to n implies S2n. So this now can be written as the probability that at time 2n you are at 0. This does not mean that you return to 0 in time 2n. This just means you may have returned earlier, right? Just that after 2n steps you happen to be at 0. May not be the first return. Times the probability that t is equal to 2n given S2n equals 0. Given that you are at 0 at time 2n, what's the probability that this is the first time that you came to 0? Right? Now this is actually quite easy. In 2n time set, was the probability that you landed back at 0? This is simply the event that you made as many left moves as you did right moves. Right? And these left moves and right moves could have been arranged however way, I don't care. Right? So this is now going to be 2n choose n times 1 by 2 raised to n times 1 by 2 raised to n. So 1 by 4 raised to n. Okay, so this is easy. Now, what is the conditional probability that t is equal to 2n given S2n is equal to 0? And how do I connect that to the ballot problem? Does anybody have a response to this?
We are consistently on right or?
Right. So if you pull out that last entry, so you have a bunch of plus ones and minus ones. Remove the last one. Suppose you removed a plus one, right? That means that in the last, what did I remove? I removed the minus one, which means plus one. Sorry. So the last displacement was to the right. The previous 2n minus 1 have n lefts and n minus 1 rights. You are looking for the probability that in this election, with n votes of one guy and n minus votes of the other, the guy who was eventually going to win remained. In other words, the random walk remained to the left through this entire thing. Same thing applies to the right, right? So by applying this ballot problem, I get that this is simply 1 divided by 2n minus 1. Okay. So this is now clean probability mass function of the return time. Okay. Now I can estimate this and I can use Karamata type integration properties because this is the probability mass function. I kind of need to integrate this over the tape to get the CCDF, which is what I'm after there. That's the idea, right? How do I do this? The way I'm going to deal with these factorials is of course using Stirling's approximation, right? So what is Stirling's approximation? Stirling's approximation tells me that n factorial is asymptotically square root 2 by n times n by e raised to n. Right? So Stirling's approximation is also an asymptotic equivalent statement of the factorial function. Right? This 2n choose n is what? 2n factorial by n factorial into n factorial. So you can plug this in. I will not do the algebra here. So you will see that I have written this down. So this 2n choose n basically asymptotically looks like 4 raised to n divided by square root 5 times n. Okay, you can do this. It's not difficult. Times 1 by 4 raised to n times 1 by 2n minus 1. Okay, so all this goes out. I'm not going to care so much about the constants anymore. So this is going to be asymptotically c divided by n raised to 3 by 2. So the square root n that came from the Stirling's part, and there was already a 1 by n setting somewhere, right? All the other constants, the pi, all that is inside c. Okay, so the PMF decays as n raised to 3 by 2. When you integrate the probability mass function, you will get a power law with an index of n raised to 1 by 2. Right? So if you are careful with the constants, you will of course get that thing. So the probability that t is greater than n is asymptotically c prime divided by square root. Right? So this is how you can argue. Again, you can do this precisely, right? I have not done this carefully, but you can account for these constants carefully and make sure that. Okay. So this is how one shows that the return time in a symmetric random walk is regularly varying with index minus half and therefore has infinite expectation. Okay. So another interesting place where heavy tails come up in the context of additive processes. Okay. Yeah. So next I'm going to talk about multiplicative processes. Okay. Here earlier we were talking about these IID random variables getting added and looking at the running sum. Now I'm going to look at cases where stuff is going to get multiplied and I look at the running product. Okay. So it turns out that when you look at running products rather than running sums, you very organically get heavy tails. Heavy tails come much more organically. Right? Even if the underlying, random variables that you're actually multiplying are not heavy tails, products very quickly and very easily become heavy tails. So I'll give you an example to this effect. And these kind of multiplicative processes, right? I'm using Pn for the running product of y1 through yn, where yi are IID and positive. Okay, these kind of multiplicative, evolutions are quite common. You might expect, right? The worth of your financial portfolio, for example, you expect it to kind of vary in some multiplicative fashion, right? Kitna kamaya is saal multiplied by your return from the next year and stuff like that. It's not additive. The way the amount of money that sits in your bank, and there's a compounding effect, right? Those things are naturally multiplicative rather than additive in nature. There are many places where multiplicative is the natural norm rather than additive, right? Any scenario where exponential growth is the natural thing as compared to linear growth, you will expect some sort of multiplicative phenomena underneath, right? So rich get richer, right? Also comes up in the same spirit. Now, multiplicative processes almost universally lead to heavy tails. Let me give you a simple example. Suppose y1 and y2 are exponential with parameter mu. Just taking the product of y1 and y2 is heavy tail. Why? Because the probability that the product of y1 and y2 is greater than x can be lower bounded by the probability that each of these is greater than square root x. That's one way for the product to exceed x, so that gives you a lower bound. And that lower bound, basically, if you substitute, you will get e raised to minus 2 mu root x. Right? It's already heavy tail. So if you just multiply two exponential IID exponential random variables, the product is already heavy tail. Right? What might you expect more generally? We just spoke about how, for example, assuming finite variance, when you look at a running sum, you get some sort of a Gaussian limit, right? Central limit here. You might expect that via a logarithmic transformation, a running product can be expressed in terms of a running sum and vice versa, right? So, you can do a logarithmic transformation to now say that log of Pn is just the sum of the logarithms of this. So log Yn, you treat that as Xn, and that now becomes an IID sum. So, which means that, okay, I'll just come straight to the punchline. So the punchline is that if originally with this process, with suitable centering and normalization, you get a Gaussian limit, you then have to exponentiate it to get the limit of Pn. When you exponentiate a Gaussian, you get a log normal, right? So therefore, with suitable, it's not centering anymore, right? Thanks to all the transformations that are happening. But via subject to a suitable normalization, the running product will actually have a log normal limit, right? Log normal is of course heavy tail, right? So, and this is true. So what is interesting about this is the following, right? So this statement that I've written here follows directly from just applying the standard central limit theorem to these log random variables. So there's no magic here as such. And but to do this, so you basically end up looking at the product divided by mu. Okay, I think there should have been mu raised to n, I believe. I think there should have been mu raised to n, but yeah. So you have some scaling, and then the whole thing has to be scaled further up, right? Now, what is interesting here is that the limiting distribution is log normal, and the mu that you end up getting here is not the expectation of the y's, but rather, and this is not difficult to see, it's actually the exponential of the expectation of the log of y. Okay, via Jensen's inequality, you can prove how this is related to the mean, but it's actually not the mean of the product. So the way you normalize has to be taken. You have to be careful that it's the value of mu and not the mean of the y that will basically dictate how whether this product is actually going to blow up or shrink down exponentially. Okay, and the condition that we have applied here, I already mentioned this mu. This condition that the variance of the log is finite is actually very, very broad, right? Because logarithm, when you apply a logarithmic transformation, you're already making the tail, you're lightening the tail considerably, right? So to say that the after logarithmic transformation, the variance is finite is not, you need really pathologically heavy tail distributions to violate that problem, that thing. In which case, then if you have that heavy-tailed a process, then you have to apply some suitable generalized central limit theorem to obtain what the limit is. Otherwise, very broadly, the limit is going to be log normal. Okay, so that's the story here. That when you have the multiplicative type thing, log normals emerge. So you might think that whenever you have some sort of a multiplicative process going on, the log normal is perhaps the natural limit to expect. But it turns out that that's not quite correct. What is correct to say is that these limiting distributions tend to be heavy-tailed, but not necessarily log normal. The nature of the limit distribution is quite fragile to small changes in the model. Okay, so if I apply a few corrections to this multiplicative process, it turns out I'll still get a heavy-tailed limit, but not log normal. I'll give you a couple of examples to this. So one possibility is that you have a multiplicative process with some lower barrier. This is meaningful for multiplicative processes with a mu that is less than 1. So they have a natural tendency to shrink. But you don't shrink beyond a certain point. There is some lower barrier that kind of keeps you from shrinking very low. Another possibility is that you just have some additive noise. Okay. Now, these are natural generalizations, and you might think that small things like this should not change the nature of the limit. It turns out that it does. You still get a heavy-tailed limit, just not log normal, right? And in fact, we should recognize what this is. So assuming that this mu is less than 1, that's not written here, and under some other mild conditions, it turns out that this Pn, right, which is basically the multiplicative pluses but with a lower barrier, right? Social security kicks in and doesn't make you poorer than a certain point, for example, right? In that case, this Pn running product with the lower barrier will converge in distribution to F, where f satisfies this condition, which we have already encountered before. That is, it's the log of f bar is asymptotically, asymptotically has a slope that's linear on a, sorry, the CCDF has a asymptotically linear slope on a log scale. Okay, so this is not, as I said, it's not regular variation. It lies in some class that's beyond regular variation, but you know that it's heavy tailed. Okay, so something very similar is also true. The same nature of the limit is also true when you add noise instead of having a lower barrier. Okay, so the point here is that if you add noise or if you change some aspects of the multiplicative process, that you get a heavy-tailed limit does not change, but the nature of the limit can change. Okay, so the log normal is not quite universal, but the heavy-tailed is universal. That's the story. Okay. So now let me move on to extremal processes. This is where we are now looking at not a running sum or a running product, but like a running max or a running min. Okay. Again, there is a well-developed theory for this, and it is interesting to understand where heavy tails emerge when one is looking at what these are called. Like, this is not extremal processes are also used in a different context, but we are also referring to these as extremal processes where I'm looking at, the running max or the running min of this sequence of random variables, right? Where do these come up? They come up naturally in many contexts. You might imagine in insurance type problems, these things will come up. If you are talking about engineering for floods, earthquakes, and so on, right? For example, in Japan, people have to worry about constructing buildings that are tall, and you want to make sure that a bad earthquake for the next 100 years should not destroy this building. So you care about understanding the likelihood of the worst earthquake in the next 100 years being worse than a certain threshold, right? And so on. Progression of world records is similar, right? You have performances of athletes that keep getting generated, and you are taking a running max of this, which max or min, depending on the context, which captures world records. Okay, so that in some sense actually gave birth to extreme value theory. For example, this also comes up in the Netherlands. Those of you who have visited the Netherlands, the place should practice it. It should, for all natural reasons, should be underwater. But through a clever engineering of dams and dikes, these people have managed to basically keep a land which is technically under sea level, livable, right? So they care deeply about rare events when it comes to ocean currents or wave heights and rare events when it comes to those kind of things, because that threatens their very existence. Okay, so question is now, how does this mn scale? You can ask this question in the same context that we have done in the past, right? Subject to suitable normalizations, what kind of limiting distributions emerge when you're looking at running max, so to speak, right? So you might look at something like this, subject to a centering divided by scaling, what kind of limit gets, right? One simple example is that of the exponential. So what's the probability that the max of this should not be greater than, it should be less than or equal to, right? When it comes to max, we will actually look at the CDF rather than the CCDF. So probability that the max is less than or equal to a and b plus bn is, of course, the probability that each of these is less than that raised to n, right? And then you can ask, well, when do you get a clean limit as n tends to infinity, and for what choice of an and bn parameters, right? In this particular case, it's possible to do this explicitly. It turns out that if you choose these ans to be 1, that's basically saying that your denominator is 1 and your numerator is log n. Okay, so which means that to a first order, if you have IID exponential observations, the running max grows logarithmically with n. So when you correct by log n, you get a limit which, as n tends to infinity, has this form. This is a CDF and not the CCDF. Once again, it's e raised to minus t. This distribution is very well known. This is called the Gumbel. Okay, so this is just one example where, with suitable centering and normalization, when you work with the exponential, entries, you get a Gumbel distribution in the limit. Okay, the Gumbel you can verify is in fact light tailed. I encourage you to try this out. Both the left and the right tails. This has an infinite support, right? It goes over the entire real line. You can actually understand By staring at that CDF, you can understand how it decays to the left and how it decays to the right. Both sides is light-tailed. Okay, so there is what one might call an extremal central limit theorem, which says what are the kind of limits that you will get when with suitable centering and scaling of this running max. This is again a well-studied problem. It turns out that this problem is not as clean as, for example, the additive or the multiplicative case. The additive or the multiplicative case, for every f with a suitable choice of centering scaling parameters, you get a limit distribution. When it comes to max, it turns out that there are many distributions for which no matter how you choose these guys, you're not going to get a limiting distribution. There just does not exist a distributional limit. Okay, so it's a bit more fragile, but it's well understood what kind of limits can emerge. Turns out that there are three categories. One of them is Frechet, Weibull, and Gumbel. Gumbel is the one that I described in the previous slide. Okay, and it's also well understood what class of distributions, what class of f will result in a Frechet limit, what class of f will result in Weibull, what class of f will result in Gumbel, and what are the choices of an and bn which would result in that convergence. All of this is also well understood. Okay, so I will simply mention the following. When it comes to running max, the Frechet, we talked about Frechet earlier. Frechet is regularly varying. You get a Frechet limit only if you start off with regularly varying x to begin with. Okay. The Weibull, remember, can be either heavy-tailed or light-tailed, and there's a class of distributions, both heavy and light-tailed, that can result in Weibull limit. Okay. And Gumbel is basically something that you get. Again, you can have both heavy-tailed and light-tailed distributions that come in. In particular, as an example, if the xi's are log normal, it turns out that the Gumbel is there. Right? So the point is that in some cases you can get a heavy tail limit, in some cases you can get a light tail limit, but it's not as clear cut as saying that if the xi's were heavy tail, then you get a heavy tail limit. If the xi's are light tail, you get a light tail limit. That's not the case. Okay. So these are So again, this is not necessarily the only interesting question one can ask about records. You can also ask what is the interval of time between records. Okay? For example, if you look at this sequence of IID entries, the points where the entry is larger than all of the entries before it is when a new world record or whatever was set, right? So you can now ask yourself, what is the gap? What is the distribution of the gap between setting of world records? Right? You might expect that as time progresses, the gap between world records should keep increasing, right? At least under the under an IID assumption, which may or may not be perfectly valid. Under an IID assumption, you might expect that the gap between world records is growing, right? Because the bar is being set higher and higher. Now you have to cross that even higher. What is the distribution of the time until a new record is set? So it turns out that this is in fact also heavy tail. In particular, let Tk be the time between the kth and the k plus 1th record. It turns out that the probability that Tk is greater than n is asymptotically 2 raised to k minus 1. Mind you, this is not IID across k. It can't be, as I said, right? Because the time between the 10th and the 11th record is going to be different from the time between the 100th and the 101st record. Right? The latter is going to be larger stochastically. So this is asymptotically 2 raised to k minus 1 by n. Okay, what does that mean? That the time between records is going to be regularly varying with an index of minus 1. Okay, now importantly, this requires absolutely no heavy tails to begin with. The distribution of the xi's can be anything. It could be bounded, it could be uniform between 0 and 1. It could be any continuous distribution. This answer is true for any continuous distribution of x random variables. With any continuous distribution, you will in fact get these heavy-tailed gaps between records. Okay, so there's a very clean proof for this, which I think, given the time, I'll probably skip. There's a neat proof, and intuitively, the idea behind the proof is that the time between records is in some sense insensitive to the actual distribution of the x. Why? Because I can apply any monotone transformation to the x's and the record times don't change, right? Now, I only need monotone transformation. It doesn't have to be linear, non-linear, कुछ भी हो सकता है. Which means that I can always, no matter what the distribution of x, I can apply a suitable non-linear transformation such that monotone transformation, such that post-transformation I get exponential. Means that without loss of generality, I can work with exponential xi's. Exponential makes my life very easy because, yeah, maybe I'll just sketch this very quickly. So you can now see the following, right? Suppose that these xi's were exponential. Let's just look at what happens to the very first entry forms a record, right? Because when you start a new sport, the very first person to play sets the world record clearly, right? So the first record is anyway just x1. Okay, and x1 is exponential with parameter 1 without loss of generality. You can apply whatever transformation you want to make sure that post transformation is exponential. Okay, now what is the probability that T1? T1 is the time before this first record gets broken. Okay, I want to understand what is the probability that this is greater than n. Okay, the way I will do this is I will condition on the value of x1. By condition on the value of x1, this T1 is basically geometric, right? So life is easy. If I condition on x1 is equal to x, then this is what? This is the probability that the next n attempts will not exceed x, right? So yeah, please correct me if I'm wrong here. It's 1 minus e raised to minus x whole raised to n. Did I do that correctly? This is the probability that those guys don't exceed x. Oh, just this, right? Is that okay? Yeah. So this is the probability that T1 is greater than. So now if I want the unconditional probability that T1 is greater than n, I just do integral from 0 to infinity. Because remember, x1 is exponential with parameter 1. Right? So I get 1 minus e raised to minus x the whole raised to n times e raised to minus x. Okay, now this is an integral we all know how to solve. This with some obvious transformation, you can write this as 0 to 1, 1 minus y raised to n dy, right? Which is what something like 1 by n plus 1, right? You will get. Okay, so this is only for the first record. Now, if you use exponential, life is actually quite easy because not only do you know the distribution of the time until which the next record is held, can somebody tell me the distribution of the second record? The first record's distribution is exponential with parameter 1. What is the distribution of the second record? Yeah. So it's basically an Erlang. It's a sum of two IID exponential ones, right? Given that you have exceeded the previous record, how much are you further going to exceed? The residual life is going to just be another exponential one, right? So it's basically a sum of two IID. It's an Erlang thing. So similarly, the kth record is going to be the sum of k IID exponential. So you can use that additional structure to basically piggyback these geometric trials over and over and over again. And basically reason about this is T1. You can reason about the subsequent ones like that. And that is what leads to this thing in the numerator. Okay, so I will stop here. This brings me to the conclusion of the second part of emergence. We talked about additive, multiplicative, and extremal processes. In the case of additive and extremal, there isn't like a universal conclusion, right? You can either get heavy-tailed or light-tailed limits depending on the underlying distributions under consideration. In the case of multiplicative processes, a heavy-tailed limit is very natural, right? So this is something that I don't have a chance to talk about now. Another quote-unquote multiplicative-like mechanism is what is called preferential attachment. Those of you who have taken a course in random graphs might have encountered this preferential attachment model. It again goes by this rich get richer type philosophy, right? You enter, like, I don't know, Twitter or something of that sort, you're most likely to follow people who are really well known. So in other words, the people who are already rich in terms of Twitter followers get richer because they have a higher chance of being followed than people who are less, right? There's a multiplicative aspect there because your popularity grows in some multiplicative fashion, and it turns out that the degree distribution that you get from preferential attachment also is regularly varying. Okay, so there's a nice and neat argument for this, which I won't have a chance to get into, but feel free to refer to the book for that. Okay, yeah. So now let me talk about estimation. Right, that's what we're going to spend the last half an hour talking about. Let me set the stage for this. At this point, we will primarily be talking about power law and subsequently about regularly varying type data. And the goal will be to perform an estimation of this alpha parameter. Right? What is alpha? Alpha is basically what captures the index of the power law. Right? In the case of an exact power law, that index is all there is with the universal with the constant sitting outside. In the case of regular variation, you have that index multiplied by some slowly varying function. But your goal is to estimate that alpha. Okay, this has been done over and over again. One of the things is that the fact that you have estimated some finite value of alpha gives you reason to believe that the data, underlying data that you are actually seeing is heavy-tailed, and specifically it is a power law with such and such index. So estimating that index is also a way of checking whether your data is in fact heavy-tailed or not. Okay. Now, what is the standard approach that people have followed in the past? Okay. What a very natural thing to do when you have data is to first plot what is called either the frequency plot or the histogram. Okay, whatever domain your data is in, you create bins within that range. You count how many samples you have in each bin, right? And then you can normalize or not, but basically you will get a frequency versus bin count type plot. Okay. Now, if you have a power law, note that even so for the Pareto, for example, not only is the CCDF a power law, the density function is also a power law, right? So if you have x raised to minus alpha in the CCDF, the density function will have x raised to minus alpha plus 1, right? So there's a even the log, even the density function of a pure power law on a log scale looks linear, except that the slope is alpha minus alpha plus 1 rather than minus. Okay. So what people do is you look at this frequency plot. By itself, it is not particularly informative. Then you transform this, right? How do I tell just by staring at this whether it's heavy or light tail? I'm going to scale this stuff. So first, I'm going to scale this on a log linear plot, which means only the y-axis is made logarithmic, the x-axis remains unscaled, right? And suppose I see something that looks, I don't know if this looks linear, but many people have in the past concluded that, well, it looks linear. If it looks linear, then it's probably light tail, right? Because exponential distributions are linear on a log linear plot. E raised to minus x, when you take log, you get minus x, right? So log linear plot mein. So you might think, well, you get linear on this, so therefore you have an exponential tail, light tail, end of story. Okay. Next, what you might do is for a different data set, you first do log linear scale and then you see, well, I don't know. Then you do some log scale and then you again see something else. And then you kind of think that maybe that's more linear than this is. So maybe it's in fact heavy tailed. And then I'm going to like fit a regression line to that data and use that regression line to estimate my alpha. Okay, so this again has been done over and over again in the past. And it turns out that so you can use regression to estimate what this tail index is. Okay, so how accurate is this approach, right? This is just some empirical thing. So one issue with this is that the histogram is the tail is already noisy because you're not getting as many samples out in the tail, right? The tail is even noisier in the histogram because every now and then you have bins where there are no samples and then you have bins with samples and no samples and so on, right? Here there's a whole bunch of bins with probably one sample or something, right? So it's already very bad. So it turns out that you don't get very good estimates from this. But one nice transformation that you can do is to not look at the frequency plot, but what is called the rank plot. What is the rank plot? You're basically looking at the empirical CCDF. You're asking yourself what fraction of samples are greater than X. Okay. Unlike binning, where you're losing information, right? Because in the very act of binning means that all data within that bin is going to basically be represented by one count in that bin. When you're plotting the rank plot, there is no loss of information. All of the data is actually going to contribute as is to the rank plot. That's the empirical CCDF. And it turns out that as you can see here, this is data from an actual regularly varying distribution. The empirical CCDF is much cleaner than the histogram, right? So if you were to do regression, which you shouldn't, you probably should do it on the rank plot rather than the histogram, right? So it turns out, for example, that if you just do a regression line on the histogram, you get an alpha hat, an estimate of alpha of 1.4, because the slope I got was 2.4, minus 2.4, that you need to make a +1 correction, that becomes 1.4. Here you get 1.9, but this data was in fact sampled from a distribution with a Pareto, an alpha of 2. Okay, so you can see that even naive regression, when done on a rank plot, is better than doing it on the histogram. Okay. So this small change is actually very important. So here is another. So this is something that has come up in the past also, right? This is on a log scale. This is the histogram of the frequency plot. Now you might stare at this and reasonably conclude that it looks roughly linear. You may even fit a regression line on this and get a very high R square value, right? Suggesting that the quality of fit is great, right? But it turns out that if you translate this to a log scale, you again get something that looks roughly linear, right? But it turns out that this data is from an exponential distribution. Okay, so the moral of the story here is that these approaches have to be used very carefully. And this kind of mistake has actually happened many times in practice. So this is from a paper in Science where they were looking at electricity grid degree distribution. They looked at the histogram on a log scale and for the frequency plot, right, with the histogram, and they said alpha is equal to 3 power law. You look at the rank plot on a log linear scale, and it looks even more linear, right? So, I mean, subsequently, more detailed analysis has shown that the original conclusion that it is heavy tail with alpha equals 3 was wrong, and this is in fact light tail, right? And some very highly cited stuff. There are other examples in the degree distribution of the World Wide Web. I mentioned this at the start, where again, this naive approach of fitting a regression line to the histogram was found to be erroneous. Okay, in this particular example, the mistake was not in the fact that it is power, in the conclusion that it's power law. The mistake was that the index was misestimated considerably. Okay, so these kind of things have happened all the time. So if you have to do regression, you should do this on the rank plot or the empirical CCDF rather than the histogram. Okay, but this is still an error-prone approach. For example, this is just data I have plotted from the log normal and the Weibull. It looks, I don't know, if you eyeball this, it might look somewhat linear. You might even get a high, if you ignore some of this data, you might even get a fairly good regression fit and stuff like that, but it's clearly not power law. Okay. Yeah, so the reason why this is error prone is that the basic assumptions of linear regression are not met here. What does linear regression assume? That your data points have IID error, right? It's neither independent nor identically distributed. When you're looking at a histogram, the fact that you have a lot of error in one bin means that has a relationship with the error that is in another bin. And moreover, the error is far from identically distributed, right? The error in the bins to the far right is considerably more than the error on the left, right? So that is why the standard assumptions based on which linear regression was actually designed were actually never satisfied in this case, right? So another approach, which is perhaps more reasonable for estimating power law bodies, if you know that your distribution is from a pure Pareto and you want to estimate the alpha, right, is to do maximum likelihood estimation. So this is actually much cleaner for estimating power law distributions, not power law tails. So what alpha will make the thing most likely, you construct the likelihood function, you can take the log of this if you want, then optimize this for alpha and so on. And if you do that, you will get something like this. The maximum likelihood estimator of alpha is n divided by summation of log of data point divided by x min. Now, to compute this maximum likelihood estimator assumes that you know your x min. So in practice, the manner in which people have done this is that you first eyeball the empirical CCDF. You see where your eyes tell you that the linear region has begun. Kill all the data to the left of that and apply it to the right of that and choose the x-min to be the threshold, to the right of which you have taken your data. Apply maximum likelihood estimation and so on, right? So if you are taking data from a pure power law, maximum likelihood estimation has nice properties, right? You have it's efficient. One can show asymptotic normality. You can prove that it's in fact you can show asymptotic efficiency and so on, right? All the nice things happen. And one interesting observation that we make is that there is in fact a connection between is regression and maximum likelihood estimation. Right? Regression people have done all the time, except that maximum likelihood estimation. So it's a way, you can think of this as a way of interpreting maximum likelihood estimation. Maximum likelihood estimation, it turns out, is not regression, but it's a special form of weighted regression. Okay, so here is the result here. The result is that asymptotically, as n becomes large, it turns out that your maximum likelihood estimator can be shown to be asymptotically equivalent to a weighted least squares regression. What does that mean? That you're weighing, when you're fitting a regression line, you're applying higher weights to certain errors as opposed to lower weights. How should you choose your weights? The weight associated with sample I is 1 divided by log xi minus x0. Now, in this case, I have sorted the data in increasing order, right? So what does this mean? As I becomes larger, the weights are becoming smaller, right? So if you are getting data from a pure power law and the noise is more in the tail, then what should you do? You should de-emphasize the error in the tail, emphasize the error in the quote-unquote body. And when you do weighted regression with those kind of weights, you are getting essentially maximum likelihood estimation. That's a way of interpreting maximum likelihood estimation, right? What this means is that in estimating, the power law parameter alpha from pure power laws, essentially maximum likelihood estimate is emphasizing the body, the observations in the body, and de-emphasizing the tail, the outliers, which makes sense because the tail is where your histogram or your rank plot is going to be more noisy, right? Again, you can do this because you're assuming that the distribution is parametrically a Pareto, right? So this is just showing that if you apply just standard least squares, you get this. But if you apply weighted least squares, so you can see the reason why it chose this red line is because of all these funny samples, right? When you apply weights, you're applying weight more on the body than the tail, so you kind of disregard this stuff better. And so you get a weighted least square of 1.5. I think the correct answer is 2, right? So when you apply, just to show that how the weights are working, that's close to what MLE would do as well, right? Emphasize the data on the body, ignore the tail, right? So this is part of the overall story that if you want to do parametric estimation of pure power loss, you should quote unquote listen to your body, disregard the tail, right? So this is where we are. You should use the log plot. You should use the rank plot rather than the histogram. If you have to do regression, you should do weighted least squares rather than unweighted regression. MLE is perhaps the most sound, statistically sound, approach to apply here. But MLE is close to weighted least squares anyway. Okay. Now, what if your data is not exactly a power law, right? As I said, exact linearity of the CCDF beyond a certain point is perhaps too strong to assume. So a natural setting from an estimation standpoint is to move away from the parametric setting where we are assuming the data is a pure power law and to move to the semi-parametric setting where we are simply assuming the data is regularly varying. Okay, so if it's regularly varying, it's asymptotically power law. So if you look at the CCDF on a log scale, eventually it is approaching some sort of a linearity, but it's not linear after a certain point. Okay, so in that semi-parametric approach, what should you do, right? If you are working with in the class of regularly varying distributions, then it turns out that, so what if, for example, your data was something like this, right? So I've used a Pareto of a certain point of a certain degree up to a certain point and a Pareto of a different one up to this. In such a case, obviously, some sort of a regression fit is going to be absolute nonsense, right? So Yeah, so one natural thing you might think, and many people have done this, is you eyeball the rank plot and then you see, okay, here is where stuff looks linear. So I disregard the stuff on the left and apply either weighted least squares or MLE to the data on the right. Right? You can do that. Issue is, where does the tail begin? Right? In general, when you have something that kind of gradually turns, asymptotically normal, you don't really know where, linearity begins and where, so that's something that is not always clean to answer. And here is just an example that shows that having a fixed cutoff can actually lead to asymptotically biased estimates. Okay, so suppose your data is obtained from a mixture of two power laws. Okay, one distribution F1, another distribution F2 with mixture probabilities Q and 1 minus Q. Okay, and suppose that alpha 1 is less than alpha 2. In other words, distribution 1 or distribution F1 has a heavier tail than distribution 2. Okay, so therefore, the alpha corresponding to this mixture can easily be seen to be alpha 1. The true alpha is alpha 1. If you add, a regularly varying distribution with parameter, with tail slope -3 and another with -2, the sum will basically be dominated by the -2. Right? So the heavier Pareto will dictate. So in this case, the answer should be alpha 1.
It will also depend on Q.
No, for any Q, this is true. Right, so I want the MLE. If I choose a cutoff, right, I apply blindly MLE to the right of that cutoff. I want ideally that alpha hat MLE should converge to alpha 1. Okay, and X-min is our cutoff. It turns out one can analyze this, that the reciprocal of the MLE will have the following limit: Q by alpha 1 times F bar 1 of X-min divided by F bar of X-min plus that other term. Point is that this, for any choice of X-min, is not equal to alpha 1. Which means that if you choose your X-min, right, you eyeball this thing, choose a certain cutoff and so on. In this particular case, for no static choice of cutoff, would the estimator that is resulting be unbiased. Okay, there is going to be a residual bias that will remain in this estimator. Right? How do we eliminate this? Yeah. So once again, when you're identifying power law distributions, you can do MLE weighted least square. These all correspond to listen to your body, so to speak. Whereas when you're dealing with power law tails, when you're working with regularly varying distributions, you have to let the tail do the talking. You have to basically let the outliers tell the story. Okay. So you use tools from extreme value theory. So once again, this is where we were. Now, with X-min as the cutoff, if you stare at the limit that you get, you will see that the bias is actually disappearing as X-min goes off to infinity. Okay? So you might think the following. Maybe the reason why this particular naive MLE approach failed was because I used a quote-unquote static threshold, a threshold X-min that did not depend on n. Right? Using a static threshold means that you are in some sense retaining for your MLE a constant fraction of the data that you have. Okay. But what does X-min going off to infinity or going off to the right as n becomes larger mean? That you are actually keeping a vanishing fraction of the data that you have. Right? So that is what you need to do in order to kill your bias. Okay. So you have this very interesting thing where you get unbiasedness by throwing away most of your data, because your threshold itself has to scale with the number of samples that you have. Okay, so X-min becomes X-min of n, where X-min of n goes off to infinity. How should it go off to infinity is the question, right? So again, choosing large X-min means that your bias is small, but if you choose a very large X-min, you are also getting higher variance because you have fewer samples out in the tail, right? So bias variance trade-off. So here is the Hill estimator. The Hill estimator is basically something that is known to work for the class of all regularly varying data settings. The Hill estimator is basically k divided by summation log of x bracket I divided bracket k. These are the order statistics. So x bracket I is the ith largest sample. Okay. So it's basically saying that I'm doing maximum likelihood estimation conditioned on the k largest samples available. Okay, it can be shown that that MLE is in fact this. Okay, now how should I set k? Now remember, if k is to grow linearly with n, that corresponds to x min being constant. I want x min to go off to the right to kill the bias. What that means is that this k, well, let's see what it means. How do we choose k? So what you want is that k by n is the fraction of data that I'm keeping. That should go to 0 as n tends to infinity. This is basically the same as saying that my threshold has to move off to the right. Except that now my threshold is data driven rather than statically chosen, right? Because I'm choosing it based on the k largest samples. So I need k of n by n to go up to 0, which means that as n becomes large, I'm going to use a vanishingly small fraction of my data sample. But k of n should go up to infinity. Because I need law of large numbers to kick in, right? Otherwise, how would things work? So you throw away nearly all your data for bias reduction, but you need still k of n to go up to infinity for consistency. So for example, k of n could grow as square root n or something like that, right? When you do that, it can be shown that the Hill estimator is in fact consistent. Okay, so the Hill estimator, so the basic principle of the Hill estimator is you can think of it as structurally similar to an MLE, except you're basically using only your k largest samples, where k is chosen in this interesting manner. That k of n by n goes to 0, fraction of samples retained is vanishing, but the number of samples retained is growing as n tends to infinity. Okay, so long as k satisfies these, it can be shown that the Hill estimator is consistent. Okay. Yeah, so throw away everything but the outliers, but in a very specific manner, right? Now the trouble is that even though you can prove asymptotic convergence guarantees as n tends to infinity, for a given data sample, if I give you data with, let's say, 10,000 points, how do I know what to choose k as? I only know that as n tends to infinity, if I choose k to scale as square root n, I'm good, things will work. But if I give you a given finite data set, how do I choose n? Do I choose k to be square root 10,000, 2 times square root 10,000, 5 times square root 10,000? I don't know, right? That is something that is not explicitly prescribed by. All we know is that no matter what times square root n, as n tends to infinity, I'm consistent. But for a finite data set, how do I choose n? That's still a bit unclear. Here is how people actually do it. What they do is they plot the Hill estimator. The Hill estimator is a function of k, how many samples you choose to keep, how many of the largest samples you choose to keep, right? You plot that versus k, that's called the Hill plot, right? And then you expect that there is some range, right, in the low end of k, where this estimator might be roughly flat, right? And where it is flat, I kind of that's the value of k I should choose, and the estimator around that is what I should do. Right? So I look for some sort of a patch where things are roughly steady, and that is how I do it. So this is in practice how people apply the Hill estimator. In spite of the fact that it has all these nice asymptotic consistency properties, in practice you end up staring at the Hill plot to decide how many to actually keep. Because if I give you a given data sample, who can tell you exactly how many samples you should choose? Right, so you choose something like this. So in this particular case, this answer is very close to being correct because this has been sampled from a distribution whose alpha is actually 2. Okay, if I just took blindly data from an exponential distribution and tried to plot the Hill plot, you see that there is really no region where the plot seems to stabilize. So it looks like things are fine. But again, yeah, there are examples. That was an artificial example where I'm basically taking 2 power laws, one power law up to a certain point and then another power law there. Again, you can see that there is a region where you are steady, and that's the correct answer. Okay, but the Hill estimate has problems too. So this, for example, is a case where there is a somewhat steady region, but depending on where you pick your k, here, your estimate will change, right? And you don't really know. No theory that tells you exactly what k you should choose. You also have examples that are called Hill horror plots, right? So these are cases where, so these kind of cases are typically obtained by multiplying some really, Atrangi slowly varying function, multiplying the power law, right? Some log x raised to 10 or something. I don't remember what this is with. No, I think this is from an empirical data set, right? And then, in the finite data set, you plotted the hill plot. How the hell do you know what case you should choose? And these kind of things do happen with the hill plot. Okay, and this data is in fact from a real world source. Okay, so this is what we said about the hill estimator. It has nice, unlike any of the eyeballing that people have done, there are nice statistical properties, guarantees that the hill estimator comes with, but to apply it in practice, there are still some issues that one has to deal with. The good thing is that there are other, so the hill estimator applies only for regular variation. There are other so-called extremal estimators in this space that in fact work on a space that is even broader than the class of regularly varying distributions, which are complementary in nature. They use different aspects of the underlying statistics to actually arrive at the answer. So the good thing is that just because the hill estimator gave you a quote-unquote horror plot does not mean that other estimators or other approaches will still be inconclusive, right? So the overall, message is that, even though the hill estimator comes with some guarantees and it's still better than eyeballing and fitting a regression line, it should be used in conjunction with other statistically sound estimators. And if there is enough consensus between these different complementary approaches, then one can reasonably believe that the underlying data is heavy-tailed and the estimator one has come up with is somewhat reasonable. Okay, so that's the message. The book, as I mentioned, so the book can be found. So if you go to my webpage, there is a link to the book, and there's a link to a webpage that the authors have maintained for the book. From there, you can actually download like a pre-publication PDF if you're interested. So yeah, I don't have the link on the slides here, but if you go to my webpage, you'll be easily able to find a link to the pre-publication. Okay, where we go through other approaches which are more robust than the hill estimator and show how they can be used in conjunction with these others. Right? So that's the overarching message, that one should not do naive estimation approaches when one is working with heavy-tailed data. There are statistically sound approaches that invoke, for the most part, extreme value theory to come up with statistically consistent estimators. And in general, one should use multiple techniques in conjunction to gain confidence. Okay. So I think that's it. I can stop here. Yeah, I can take questions if there are any.
While estimating power law tails, you said that somewhere that X-Men as X-Men tends to infinity, it removes the bias. I didn't understand that.
Oh, yeah, I didn't go into the details of that. One has to explicitly compute what the limit of that estimator is as n tends to infinity. And it turns out that this ratio, right? See, what's happening is that as x, so this is the CCDF of F1, this is the CCDF of F. Okay, so it turns out that because F1 is the dominant tail, F2 by F bar will essentially go to 0 as x min goes to infinity. This term will vanish. And then this term, there's a Q sitting here, of course, which is basically what this ratio will be as x tends to infinity, and you will end up with x1. So that's the reason why. Because F2 is a lighter tail than F1, as x min goes to infinity, with the mixture defined the way it is, the estimator will in fact converge to the correct answer. That was just a way of motivating that you have to basically move the threshold to the right, which the hill estimator is indirectly doing by scaling the number of largest samples it keeps in a certain
Efficiency diagram of the example you have provided, they have shown that the first heating time is the distribution of first heating time is a heavy-tail distribution.
Return time to 0, you mean? Yeah.
Can you say anything like other heating times, like second, third, or heating times?
So it's Markovian, no? So see, the time between the first and the second hitting time, return time to 0, is identically distributed to the time from the second and to the third to the fourth, and so on, right? It's basically, I mean, if you look at the instance where you visit 0, that defines a renewal process. So the times, return times, if you will, these are in fact IID, but they are IID with an infinite mean. Right? So yeah. You have to be careful when applying renewal reward or something like that. But the mean cycle length, so to speak, is infinity.
Is the assumption that it's coming from only F1? Only in those cases it's going to
Oh, depends. So this calculation is assuming this particular form. In the previous setup, that MLE was assuming Pareto. So exact power law beyond X-min.
and it's proved that it's optimal. MLE is
Yeah. So it matches the Kramer-Rao lower bound. So asymptotically, the variance is optimal.
There is a notion of M estimates, bogus statistics with it.
Okay.
So is that connected to weighted least squares formulation of this formulation?
I don't know. Yeah. I mean, if you explain what that is, maybe I can talk about it. But yeah, I don't know what that is. Any questions on the online side? Okay, all right. Thank you very much.
issue in between.
Okay. Yeah. All right. Yeah. Thank you very much, guys.
It's a this month. Okay.
Thank you so much.